So in this lecture, I would like to discuss about the topic related to solutions. So what are the solutions? Solutions are various types. Solution is a homogeneous mixture of solute and solvent. A binary solution is a homogeneous mixture of a liquid solute in a liquid solvent. That is a solution of liquids in liquids. Solutions of solids in liquids and solution of gas in gas. Number of types of the solutions are there. But in this topic, I would like to discuss about the solutions of liquids in liquids. Solutions of liquids in liquids. So what is a solution of liquids in liquid? Very simple. A binary solution, binary means two, is a homogeneous mixture. Mixture should be homogeneous of liquid solute in a liquid solvent. For example, solution of ethanol in water. Take 50 ml ethanol and 50 ml water in a beaker. 50 ml ethanol and 50 ml water in a beaker. Then in a beaker, you cannot identify which is water and which is ethanol. The solution is completely miscible. And that solution is called as solution of ethanol in water. Only one layer is there. It is a homogeneous mixture. So this is the solution of liquid in liquid. Many examples we can give belongs to this. Solution of methanol in water, solution of carbon tetrachloride in ether, solution of acetone in ether, where there is a formation of homogeneous mixture, only one layer. Actually, there are 9 types of solutions. How many types? 9 types of solutions. Solutions of liquid in liquid is one of them. Okay. The binary mixture is obtained from any two liquids. You can take any two liquids, and if that two liquids are mixed up, and if there is a homogeneous mixture, then the solution can be formed. Now, there are 3 types. Solution of liquids in liquids are 3 types. First one, it is completely miscible liquids. Just we have taken the example of ethanol in water. Okay, here. So it is a completely miscible. Both are completely miscible to each other. So this is the one type of the solution, completely miscible liquids. Partially miscible liquids. Example, it is phenol in water. Partially miscible. Some phenol, it is mixed up with water, but there are 2 layers can be seen. It is not homogeneous. Solution of phenol in water, it is not homogeneous. But some phenol, it is mixed up with water. So this is partially miscible liquids. And third type of the liquids, it is completely immiscible. Suppose that if you take water and oil, so oil is not miscible with water. It is completely immiscible, even though not partially miscible. Or you can take kerosene in water. The 2 layers are distinct there. Petrol in water, 2 layers are distinct there. So completely immiscible liquids, example it is given here, iodobenzene and water. nitrobenzene and water. They are completely immiscible, means you can distinctly see the two layers there. Okay, one layer it is belongs to iodobenzene and one layer is belongs to water. The liquid which is having higher molecular weight, it will be at the lower level, and the liquid which is having lower molecular weight, it is at the higher level. So these are the three types of the solutions of liquid in liquid. And in this lecture I would like to discuss about solutions of liquids in liquids. So completely miscible liquids, both the liquids are completely miscible. Solution is homogeneous, only one layer is there. Example is alcohol in water. Partially miscible liquids, one liquid it is partially soluble in other liquid. Example it is phenol and water. And third one, it is completely immiscible liquid, that is iodobenzene and water. Now in this chapter we are talking only about completely miscible liquids. Okay, not these two, partially miscible and completely immiscible. So completely miscible, miscible means soluble, completely soluble, homogeneous mixture. So in a binary solution means mixture of two. The amount of its constituents can be varied to any extent, till the system will always lead to a single liquid phase. The constituent liquid molecules do not interact with each other. Generally, we know that when we prepare the solution, there will be no any interaction between the solute and the solvent. Actually, solution, it is a homogeneous mixture of solute and solvent. Solute and solvent. So in this case, water is a solvent, ethanol it is a solute. Okay, and the ethanol and water cannot be interact with each other. Means there is a no chemical reaction. During the preparation of the solution, there is a no chemical reaction, only we get the solution. You can take another example. Solution of sodium chloride in water, solid in liquid. This is also homogeneous solution, but sodium chloride does not react with water. Remember this. Okay, the two constituents of the solution does not react with each other. Okay, now the solutions obtained from mixing of completely miscible liquids are of two types. First one, it is ideal solution or perfect solution, and second one, it is a non-ideal solution or real solution. There are two types of the completely miscible liquids. One, it is ideal solution or perfect solution, and second one, it is a non-ideal solution or real solution. So in this lecture we are discussing about the solutions, particularly solutions of liquids in liquid. There are three types of the solutions of liquids in liquids: completely miscible liquids, partially miscible liquids, and completely immiscible liquids. In that three types, we want to discuss about only completely miscible liquids. Okay, so now there are two types of the completely miscible liquids: ideal solution and non-ideal solution. Let us discuss about the ideal solution. Actually, ideal solutions are very rare, because to satisfy the condition of the ideality, it becomes very difficult. To satisfy the condition of the ideality, it becomes difficult. Just like suppose that ideal student. So to satisfy the condition of the ideal student, that becomes very difficult. So there are very rare students can satisfy that conditions. Then we can say that that student is an ideal student. So similarly, in this case, ideal solution, we want to discuss about ideal solution. So let us going to be discuss the thermodynamics of ideal solutions. thermodynamics of ideal solutions. So the first topic which is related to that, that is a Raoult's law. Raoult's, it is the name of the scientist. Thermodynamics of ideal solution means what are the conditions are there, and that condition should be satisfied by that solution, then and then we can say that that solution becomes an ideal solution. So we are talking about completely miscible liquids, and first type of the solution, it is ideal solution. Okay, so let a solution containing several liquids in equilibrium with vapor phase in a closed vessel at certain temperature. Consider constituent I both in gas and solution phase. Suppose that there are several liquids we have taken. So in gas phase, the chemical potential, this mu I, what is this? Mu I in gas phase. Suppose we have taken several liquids, okay, ethanol, water, and above this there are some vapors are also, means gas phase, and this is liquid. There is a equilibrium of liquid with vapor. So the chemical potentials, we know the derivation of the chemical potential in the chemical thermodynamics. We have derived this derivation, mu it is equal to mu 0, mu it is equal to mu 0 plus RT ln F. Okay, so suppose there are I constituents are present into the solution, then we can write mu I, it is equal to mu I 0 RT ln Fi. Okay, so this is for in gas phase. Similarly, for the liquid phase, you can write the same equation in this way, mu I liquid equal to mu I 0. What is your mu I 0 or mu 0? It is a standard chemical potential. Mu, it is a chemical potential. We has been discussed the definition of the chemical potential in the chemical thermodynamics. And mu 0, it is the standard chemical potential. When the standard conditions are maintained, then that potential is called as standard chemical potential. So these are the two equations already known to us. So mu equal to mu 0 plus RT ln Fi, and for a liquid state we can write A, activity, we cannot write fugacity. We can express the activity of the solution, and in the gas phase it is fugacity. F, it is a fugacity, okay, and A it is a activity. So these two equations are there, where mu I 0, it is the standard chemical potential of the ith constituent, Fi, fugacity of ith constituent, Ai, activity of I constituent. That is the meaning of the each term. At equilibrium, the chemical potential of constituent in both the phases must be same. Okay, at equilibrium, suppose that there is a equilibrium between the liquid phase and vapor phase. This is liquid phase and this is vapor phase. Okay. We know that the liquid has a tendency to goes into the vapor state. Okay, suppose you take water here. Water has a tendency to goes into vapor state. So there are some vapors are here, and that vapors create the vapor pressure. So at equilibrium, the chemical potential of the constituent in both the phases must be same. It means the chemical potential of the liquid phase becomes equal to the chemical potential of the gas phase. We can write in this way, at equilibrium. If there is a equilibrium between the two phases, then there is a equilibrium between the chemical potential, there is a equilibrium between the free energy. Okay, so we know that mu I gas phase, it is equal to mu I liquid phase. So we can substitute that equation now. Okay, we know that mu I of the chemical potential of the ith component of the gas phase, it is equal to mu I 0 plus RT ln Fi. This is known to us. So this becomes equal to this. So actually the chemical potential, standard chemical potential in both the phases are same. It cannot change, get cancelled. Both the values are same. This RT get cancelled. Ln it is on to the both side. So we can take the now ratio here, Fi it is equal to Ai. So Fi upon Ai it is equal to Z. It is a constant. It is a constant here. Fi it is the fugacity of the ith component and Ai it is the activity. Fugacity is when it is for the gas phase and activity for the liquid phase. So it is equal to Z. In the pure state of the constituent, if that constituent it is pure, then fugacity of the ith component it is equal to standard fugacity. Fugacity becomes equal to the standard fugacity and activity becomes equal to 1. When a liquid it is into the pure state or when the gas it is into the pure state, then activity can be taken as unity, pure state or standard state, and fugacity it is equal to standard fugacity. So remember this. So in the pure state of the constituent, Fi it is equal to Fi0 and Ai it is equal to 1. Hence this equation can be written now. Okay, Fi upon Ai it is equal to Z. It is a constant. So it is equal to, so Ai it is equal to 1 here and Fi it is equal to Fi0. So Fi0, Z it is equal to Fi0. So we can put the value of the Z here, okay, into this equation. So therefore we can write here Fi upon Ai it is equal to Z, that is Fi0. Okay, because Z it is equal to Fi0. So we can write according to this. So therefore Ai activity it is equal to the ratio of this Fi upon Fi0. Fugacity of the ith component divided by fugacity of the ith component in the pure state, Fi0 it is equal to. So in this way we can find out the activity. Fugacity for the gas phase, remember this. So activity it is the ratio of the fugacity in the pure state to the fugacity in the standard state. Sorry, fugacity in the normal state divided by fugacity in the pure state. So this is equation 1. So in this way we find out here the derivation of the activity. Activity it is the ratio of the two, Fi upon Fi0. Now when the system behaves ideally, the solution is ideal. Fugacity may be replaced by partial pressures. Instead of writing the fugacity, we have to replace the fugacity by the partial pressure. And activity may be replaced by mole fraction. Activity may be replaced by mole fraction. Okay. Activity can be replaced by mole fraction here. So the above equation can be written, means this equation, Ai it is equal to Fi divided by Fi0. So if the system is ideal, solution is ideal, fugacity may be replaced by partial pressure. For the gases, we can express concentration of the gases in terms of pressure. Okay, and activity replaced by mole fraction, this Xi, mole fraction, the term to explain mole fraction, it is Xi. When it can be possible, if the solution is ideal. If the solution is not ideal, then we cannot do this. Therefore, for an ideal mixture of liquids, the equation 1 can be written as this, like this. It is possible only for ideal mixture. Activity can be replaced by mole fraction. Mole fraction, it is the term to express the concentration of the solution. Activity, it is also the term to express the concentration of the solution. Okay. So instead of writing Fi, we write here Pi, partial pressure of the ith component, and Fi0, it is Pi0. So this is the modification of the equation 1. Now this is equation 2, and this is for ideal solution. If the solution satisfy the condition of the ideality, this ratio is also changing now, where Pi is the vapor pressure of the ith component in the solution. Pi0, it is the vapor pressure of the ith component in the pure state, and Xi, it is the mole fraction of the ith component, mole fraction of that component. So equation 2 can be written as, we can write this equation now. So partial pressure Pi, it is equal to Xi into Pi0. Pi0. Suppose that in a solution there are two components, A and B, ethanol and water. Then we can write here this derivation for ethanol. For A component, Pa, it is equal to Xa into Pa0, or Pb, it is equal to Xb into Pb0. Okay, we can modify the equation. So the equation 2 can be written as Pi, it is equal to Xi into Pi0. Equation 3 states that vapor pressure of a volatile constituent. This Pi, it is a vapor pressure. Vapor pressure of a volatile constituent in a solution is equal to its vapor pressure in the pure state. This Pi0, vapor pressure in the pure state, multiplied by its mole fraction. Multiplied by its mole fraction in the solution. Temperature remaining same. This statement is called as Raoult's law. Raoult's law states that the vapor pressure of the volatile constituent in a solution is equal to its vapor pressure in the pure state multiplied by its mole fraction in the solution. So this relation has given by the Raoult's, hence it is called as a Raoult's law. Very, very important. Okay, applicable for ideal solution. So Pi, is equal to Xi into Pi0. Okay, the partial pressure or vapor pressure of a volatile constituent in a solution is equal to its vapor pressure in pure state multiplied by its mole fraction, whatever its mole fraction are there. Let us see. Two liquids, ethanol and water. Okay, ethanol and water. Suppose that it satisfies the condition of the ideality. Then we can write the Raoult's law for the component ethanol. So partial or vapor pressure of the ethanol, Pe, it is equal to mole fraction of the ethanol into the vapor pressure in its pure state. When it becomes pure, then the vapor pressure can be written as P0, pure state, vapor pressure of the liquid in the pure state. So we can write the equation for the ethanol. For the water, we can write the equation now. Pw, it is equal to Xw, mole fraction of the water, into this. So in this way, we can write the Raoult's law. But when the system behaves ideally, If the solution is ideal, then we can write this equation. Pi it is equal to xi into Pi0. Okay. So the equation states that the vapor pressure of the volatile constituent in a solution is equal to its vapor pressure in pure state. So in this way, we derive the derivation for the Raoult's law here. The derivation for the Raoult's law, it is derived here. Let us see here. The equation 3 is the another definition of the ideal solution. Equation 3 is the another definition of the ideal solution. That is the solution which obeys the Raoult's law, which satisfies the Raoult's law at all concentration and temperature is called ideal solution. Okay. That is the partial pressure or vapor pressure of the pure vapor pressure of the component, that is Pi, it is equal to, it is the product of Xi and Pi0. So this is the Raoult's law, and the solution which obeys this Raoult's law, that solution is called as ideal solution. Otherwise that solution, it is not called as ideal solution. Try to understand about this. So a solution is said to be ideal when that solution has to be satisfy the condition of the ideality. Okay. So this is about the ideal solution and Raoult's law. Okay. So I think you can understand about these solutions. In this lecture, we has been discussed about what are the solutions, and particularly the solutions of liquids in liquid. So a binary solution is a homogeneous mixture of liquid solute in liquid solvent. For example, solution of ethanol in water. Actually, there are 9 types of the solutions, but in this case, we want to discuss only the solution of the liquids in liquid. The same can be applicable to the solution of solids in liquid, solutions of gas in liquids, like that. But in this topic, we have to discuss about solution of liquids in liquid only. So there are 3 types of the solutions of liquids in liquid: completely miscible liquids, partially miscible liquid, and third one, it is completely immiscible liquid. Okay. So we are talking about completely miscible liquids. Completely miscible liquids. There are 2 types of the solutions belongs to this: ideal solution and non-ideal solution. Then we explain the thermodynamics of ideal solutions. Okay, thermodynamics of ideal solutions. And according to the definition of the chemical potential, we know the derivation mu, it is equal to mu 0 plus RT ln F. That is for gas phase. And in the solution phase, it is mu, it is equal to mu 0 plus RT ln A. Because in liquid phase we can express the activity, and in gas phase we can express the concentration by fugacity. So on the basis of these 2, we derive the derivation of the Raoult's law. At equilibrium, the chemical potentials are same. So we write the equations: chemical potential of the gas phase equal to the chemical potential of the liquid phase, as we have shown here. Chemical potential of the liquid phase, it is equal to the chemical potential of the gas phase at equilibrium. So we can write this taking the ratio Fi upon Ai, it is equal to Z. In the pure state of the constituent, Fi it is equal to Fi0. When the liquid or when the gas, it is in the pure state, then fugacity of that component becomes equal to the standard fugacity Fi0, and activity becomes equal to 1. In the pure state, the activity of that liquid becomes equal to unity, or in the standard state, the activity of that liquid becomes equal to UNG. So this Ai, it is 1 here, Fi it is equal to Fi0, Fi it is equal to Fi0. So Z it is equal to Fi0. So we can write here Fi upon Ai it is equal to Fi0. So activity, it is the ratio of the fugacity. AID is equal to Fi upon Fi0. So this is the equation 1 here. Activity, it is related to the ratio of the fugacity. Activity, it is related to the ratio of the fugacity. Now when the system behaves ideally, if the solution is ideal, fugacity is replaced by partial pressure. No need to write the fugacity there. If the solution is ideal, then we can replace the fugacity by the partial pressure. Means an activity by the mole fraction. Then we can write the equation 2 now. Xi is equal to Pi upon Pi0. And from this we can write Pi is equal to Xi into Pi0. So this is the Raoult's law. This is equation 3. And it is a Raoult's law. So in this equation, Pi, it is the vapor pressure of the component I in the solution. Pi0, it is the vapor pressure of the component in the pure state. And Xi, it is the mole fraction of that component. Okay. Suppose if we have taken the mixture of this ethanol and water, then mole fraction of the ethanol, mole fraction of the water. Okay. So the equation 2 now can be written in this way. Pi is equal to Xi into Pi0. That is the product of mole fraction and the vapor pressure of the liquid in the pure state. Pi0, it is the vapor pressure of the liquid in the pure state. So thus equations 3 states that the vapor pressure of a volatile constituent in a solution is equal to its vapor pressure in the pure state multiplied by its mole fraction. Multiplied by its mole fraction. What is the meaning of this? म्हणजे जर समजा तुम्ही दोन लिक्विड घेतलेले असतील तर एका लिक्विडचा व्हेपर प्रेशर, the vapor pressure of a volatile constituent of that liquid in a solution is equal to its vapor pressure in the pure state multiplied by its mole fraction Xi, temperature remaining same. This statement is called as Raoult's law. So this is a very, very important statement of the Raoult's law. So thus today we derive the derivation of the Raoult's law. We derived the derivation of the Raoult's law that is applicable for the ideal solution. And if the solution is ideal, if the solution is ideal, and to satisfy the condition of the ideality, the partial pressure of that component, whatever that component, it is equal to mole fraction of that component multiplied by the vapor pressure of that component into the pure state. So this is the Raoult's law. This is the Raoult's law. Suppose that there are two liquids are given A and B. So for the liquid A, we can write the equation now. Partial pressure of the liquid A becomes equal to the mole fraction of the liquid A multiplied by the vapor pressure of the liquid A in the pure state. Similarly, for another liquid B, we can write the equation now. Pb, it is equal to Xb, mole fraction of that component multiplied by vapor pressure of that component in the pure state. So this is the Raoult's law. So if this Raoult's law is satisfied by the liquid, then the liquid is said to be ideal liquid. So it becomes very difficult to satisfy the condition of the ideality. Okay. So now I would like to stop here. Okay. I would like to stop the lecture now. And